let's talk about the concept of a vector space. A vector space is a collection of objects, which we call vectors, and these vectors can be added together or they can be multiplied by scalars. So formally, we define a vector space over a so-called field, which I denote here by F. If you don't know what a field is, you can just think of the set of real numbers. And this vector space, which we denote by V, is a set, and it comes with two operations, addition and multiplication. And these two operations have to satisfy several axioms, which I've listed here. So we have associativity. So if you have three vectors, you can do U plus V, and then add W, or you can do first U and first add V and, plus W. You have commutativity, where U plus V is equal to V plus U. You have an identity, so that means you have a zero element, which if you add it to a vector U, you get back U. And then finally, you have an inverse, which is here denoted by minus U. So if you add U to minus U, you simply get 0. Okay, so simple axioms that we use all the time. And let's just look at an example of a vector space, which is R2. So R2 is essentially defined as a set of ordered pairs of real numbers. So think of X and Y, right? So here, X is in R, and Y is also in R. And then we can define operation on this vector space R2. So we, again, here have a vector, which is a concatenation, let's say, of two scalars, right, x1 and y1, and we want to add it to another vector, x2, y2. And what we do is for the simple entry, we simply do x1 plus x2, and the second entry, we simply do y1 plus y2, right? So very, very simple things. And we can, as I said, right, the other operation is that we want to multiply by scalars. So if you take a vector, you multiply by a scalar, you simply have to distribute, right? So you do a times x for the first entry and a times y for the second entry. Okay. So once we have a vector space, we typically want to equip it with a norm. So this norm is something that will allow us to essentially measure certain quantities in this space. So let's look into it more formally. So a norm is defined again for a vector space, which we denote by V. And this norm is going to be a function from this vector space V to the set R, to the set of real numbers. And this norm is essentially going to be a non-negative valued scalar function, so which here I will denote by P, right? So P is our norm, and it goes from the vector space V to here the set of positive numbers. And it has to satisfy the following properties. So first of all, it's not negative, right? So for any V, PV is greater or equal than 0. If it's 0, that implies that the argument V itself is 0. It has this property that, again, when we multiply by scalars, so if you take the norm of A times V, it's simply the absolute value of A times the norm of V. And then one fundamental property that we will be using very often is a triangle inequality. If you want to take the norm of the vector U plus V, it's upper bounded by the norm of U plus the norm of V. So when we apply this to, for instance, vectors, so what I discussed so far was a bit abstract. Now let's just apply it to, for instance, vectors. So now you have a vector V that lives in some vector space. And then we have here the same exact properties that I've just presented. So now it maybe makes more sense because you're a bit more familiar with this concept of norm, right? So we have the non-negativity, the scalar multiplication, and triangle inequality here as well. So what are examples of common vector norms that we will be using? The most common one is the 2 norm, so the Euclidean norm. Essentially, what you do is that you take the sum of the square of the entries of the vector, right? So V is a vector, it has these entries here. You sum over all entries, so we have n of these entries. We sum over all of them, and we square. And here you have a square root, right? So this is the Euclidean norm. We also have this 1 norm, which essentially, instead of taking the square, you just take the absolute value of the entry. And the infinity norm, where what you do is that you take the maximum value, or the maximum absolute value of the vector. Okay. We can also define the concept of matrix norm. So this is also based on the concept of vector norm. So let's say that we have a vector norm that is defined on Rm. And we define a matrix A here, which is an m by n dimensional matrix. And to define the so-called operator norm of this matrix here, we do the following. So here I denote this with a general P norm. So what you can already see inside here is that I have a general P norm for now. In below here, you can essentially just replace P by 2. So if you rather look at this here, for instance, we just say we are looking at the Euclidean 2 norm, which I've just presented before. And the way that we define this, this matrix norm in the case of P equal 2 is to take the supremum of A times X, right? So A here is a matrix, X is a vector. Therefore, this is a vector. So we are looking at the norm of a vector here. And then below, we normalize by the norm of this vector X here, okay? And here, importantly, right, so this is valid for, we take the supremum for all X in Rn. Of course, we have to exclude X0, right? Otherwise, this will not be defined here. Okay, and we take the supremum over all of these vectors X here. And this is how we define the so-called operator norm, which is also related to what I call S1 of A, which is the largest singular value of A. We will have a review of singular values as well. So I will defer this to a bit later if you don't know what it is. But this is now how we have defined the concept of a matrix norm. Finally, I want to conclude this short section here by discussing an inequality that is called Cauchy-Schwarz inequality. And this would be convenient for us when we have to derive various bounds on inner products that involve inner products. So what this inequality says is that let's take two vectors, X and Y, and you take the inner product, and then you look at the absolute value of this inner product. And it says that we can bound this simply by the norm of X times the norm of Y, okay? You can also write this in a coordinates fashion if you like, right? This is just writing the definition of the inner product here. So it is equivalent. I have various proofs in the lecture notes. If you want to look at it, it's rather simple. And again, this is something that we'll be using often during the semester.